Okay, everyone, welcome back. We are doing the first task of this week, week 9. Let's do a bunch of problems from the textbook on area, and we learned about finding the area between two curves the previous week, but we just did a couple problems, and now we're doing a couple more. So I think this topic is important enough that we have to do a bunch of problems, and so I pushed some on to this week. Okay, here we go. I'm going to go over all of them right now. The first problem is pretty straightforward and maybe not that exciting. It says take the function f of x equals x e to the negative x squared and find the area, let's see, the exact words are between it and y equals 0, the line y equals 0, between 0 and 1. Okay, so I didn't know exactly what this curve looked like, but I knew that its end behavior was going to be 0, so I knew it was going to, because that denominator is getting very, very big as x goes to infinity. So I looked at a graph of it. Also, you could, if you wanted to, this is not really what we're doing now, but you could, if you really, really needed it, you could always differentiate this function, which I did over here, and I determined that it has a relative max at root 2 over 2, so there it is. Okay, but probably no one is going to do that. What are we going to do? We're going to find the area of this green shaded region. And here I think there's not that much going on. How do you find the area of this region? You just divide it up into an infinite number of little rectangles. And so I draw the representative rectangle here. For a given x value, it's going to have the height of the function. And so, okay, this problem is just not that much going on. It's just going to be the integral from 0 to 1 of x e to the negative x squared dx. The height of the rectangle times the width of the interval, which is dx. Okay, so now it's just, can we do this integral? Yeah, we can. We should do a substitution. So let's let u be negative x squared. Yeah. And then du dx is negative 2x, and so du is negative 2x dx. And there is an x dx in there, so I need to stick in a negative 2 and undo the damage with a negative 1/2 on the outside. And therefore, this whole thing becomes negative 1/2 negative 2x dx is du, and then that becomes just like e to the u du. And then I change the limits. When x is 0, u is 0, but when x is 1, u is negative 1. Now I will do the thing that most people do in this situation, which is they flip the limits of integration, so we're always integrating from the smaller number to the bigger number. So that becomes 1/2 integral from 0 to 1 of e to the u du. And okay, this is just easy because the antiderivative of e to the u is just e to the u, and so we got a kind of this type situation. So this is 1/2 e to the 1 is just e minus e to the 0 is 1, and so there's our answer right there. Okay, good. One down, bunch to go. That was maybe kind of a warm-up problem. Not that exciting, but the next problem is a little bit exciting in that it is a multi-step problem where with a lot of sort of thinking involved. Okay, so here we go. 69. Next problem, or next this very next problem says, here are the directions exactly. Set up and evaluate the definite integral that gives the area of the region bounded by the graph of the function and the tangent line to the graph at the given point. Okay, so here we go. Our function is f of x equals 1 over x squared plus 1, and then there's some point given, 1 comma 1/2. And the directions, once again, find the area of the region bounded by the graph of the function and the tangent line to the graph at the given point. So first, just confirm maybe that this problem is correct, because what is f of 1? Well, yeah, it is 1/2. So 1 comma 1/2 is a point on this curve, and we need to find the area of the region bounded by the graph of the function and the graph of the tangent line to the function at that point. Okay, so first of all, what even does 1 over x squared plus 1 look like? Well, this is something that we've seen several times before, but just for kind of recap, you know, you should be thinking, all right, this is what x squared looks like, so x squared plus 1 is going to look like this, moved up 1, and then for the reciprocal of that, we just sort of perform the reciprocal transformation. The reciprocal of 1 is just 1, and the reciprocal of things bigger than 1 is smaller than 1, etc. Okay, so that was sort of the thinking. I'll just leave that up there on the board. Really, the picture is, and I'll try to make it sort of big here. Yeah, really, the picture is kind of like this. So, really, that's not even that big. Okay, and 1 seems to be an important point. So when I plug in 1, I get 1 comma 1/2. Or I get 1/2 out of that. Okay, so there's my graph. What am I supposed to be doing again? Oh yeah, I'm supposed to be finding the equation of the tangent line to the graph at the given point. So it's hard based on my picture to sort of see, but there is the tangent line, and for this I need to do some differential calculus. So how do I find what do I need to know about this blue point, this blue line? I need to know the slope, and okay, it goes through 1 comma 1/2, so I really just only need to know the slope. In other words, I need to differentiate this function. So okay, I have my function. It's probably best written as x squared plus 1 to the negative 1, and then the derivative of it is negative x squared plus 1 back inside for the derivative of x squared plus 1, which is 2x. And perhaps that's just best written as negative 2x over x squared plus 1. Sorry, to the negative 2. That was just like all wrong what I said. Let me just double check that. The function is x squared plus 1 to the negative 1. The derivative of x squared plus 1 to the negative 1. The derivative of something to the negative 1 is negative 1 something to the negative 2 back inside for the derivative of x squared plus 1, which is 2x. Yeah, that's good now. Okay, so if that's the formula in general for the derivative, what is the derivative specifically at 1? Well, I now plug 1 into my formula, and I get negative 2 over 2 squared, which is 4, so this is negative 1/2. Okay, so what have I just learned? I've just learned that this blue line has slope equal to negative 1/2. And actually, you can kind of just eyeball right now that since it's more than eyeball, it's you can reason that since this y-intercept is 0, 1, then in fact this blue line is going to go through that point 0, 1. So this tangent line, this line which touches the curve at just 1 point locally near x equals 1, in fact touches the curve again at 0, 1, because that's just the line. If the slope is negative 1/2, then sort of down 1/2 over 1. Okay, if you if you didn't notice that, then you have another method, of course, at your disposal, which is to write the equation of that blue line. What is it? I'll do it in blue. It's y minus 1/2 equals y minus 1/2 equals negative 1/2 x minus 1, and so perhaps we would just write it as y equals negative 1/2 x. That's plus 1/2 plus another half, so just plus 1. So that's the equation of the tangent line, and okay, we can just see already that it has y-intercept 1, as I was saying. But if you really wanted to sort of do this analytically, you could solve for the points of intersection, because after all, the problem is asking us for the area of the region bounded by the function and its tangent line. So what are the points of intersection between this function and maybe it's best to write this as negative x plus 2 over 2, if I did that right. well, to solve this equation, I could, I guess, this seems a little silly now, I could just solve this, I guess. So I get x cubed plus 2x squared minus x plus 2. And indeed, this just gives me x squared plus 2x. Let's see, something went wrong. What happens? 2 equals negative x cubed plus 2x squared minus x squared. Yeah. So really this is like negative x, or, okay, sorry. Cancel the 2's and this becomes x cubed minus 2x squared plus x. And that is x squared minus 2x plus 1. And so, okay, this is not particularly helpful, but what I've just done is I've solved for the point of intersection and I found is that 0 and 1. And in fact, there's something sort of mildly interesting here, which is this equation that I just solved is, what was I doing again? I was solving for the points of intersection of the function and the tangent line. And what I found is that they intersect at 0, okay, I knew that already, and x minus 1. I knew that already. But it's a little bit interesting because, in fact, this equation has like a double root at 1, which is to say that this line is intersecting this curve sort of double root style or something like that at the point 1 comma 1/2, or at the point x equals 1. Okay, so after all that work, what we've essentially discovered is, dude, this picture is just totally correct, and therefore the task was to find the area of the region enclosed by the graph of the function and the tangent line to the graph, which means, okay, you can probably barely see it, but what it means is that it's this green stuff that we are going to be finding the area of, this green region. How can I find the area of this green region? Well, I shall partition the interval up from 0 to 1 up into subintervals, choose an arbitrary x value, and then draw the representative rectangle. And the height of that representative rectangle is the difference in the y coordinates between the top function and the bottom function. Okay, so after all this, I get that if I just take 1 over x squared plus 1, the height of the top of the rectangle, and subtract the height of the bottom of the rectangle, which will be the y value of the tangent line, so that's negative 1/2 x plus 1, then that expression gives me the length, or the height, I guess you would say, of that rectangle. And if I multiply by the thickness of the rectangle, which is dx, then I just integrate from 0 to 1. Alright, so this whole problem is really just, dude, what's the integral from 0 to 1 of 1 over x squared plus 1 plus 1/2 x minus 1. And this is just easily done. Because I can antidifferentiate these things term by term. The antiderivative of 1 over x squared plus 1 is arctan, so that's arctan x. The antiderivative of 1/2 x is x squared over 4, I guess. And then this is minus x. And then this is all at 1 and 0. Well, arctan 1 is pi over 4, and that's plus 1/4, and then minus 1, and then these are all 0 when x is 0. So what I really get is pi over 4 minus 3/4. And of course, pi is just a tiny bit more than 3. So this is a very tiny number. It's a quarter of the difference between 3 and pi. Okay, good. That was just one problem. But anyway, okay, we continue. Oh man. Mm-hmm. 73. Let's do it. What is it? It says, oh, this was the thinking problem. 73 says a college, yeah, let me draw this. A college graduate, a college graduate has 2 job offers. The starting salary for each is $32,000 a year. Okay, this textbook is quite old, but all right, people still make that much money in the world, and after 8 years of service, each will pay $54,000. So, okay, 54. The salary increase for each offer is shown in the figure from a strictly monetary viewpoint. Which is the better offer? Explain. Okay, so this is, I think, a great problem. There's not really anything to do. This is just a sort of a thinking and understanding problem. And it's possible, actually, that this is just total common sense, and this is just completely obvious to you. But you would be surprised at how many Americans do not understand or appreciate this. So you have, this is offer 2. And this is offer 1. And what are we actually looking at? Well, we're looking at this x-axis is time in years, and the y-axis is salary. And the salary is in dollars per year. Okay, so you could say that it's kind of a rate function, so to speak. It's the amount of money you're being paid per year, and you can see that both of these jobs, okay, this is in some sort of industry, maybe like teaching, in which you get hired and sort of regardless of performance, you're going to receive very specific set in stone salary increases each year up some kind of salary scale based purely on how long you've been working. And that's all published sort of like well in advance, union negotiated, standardized for all employees. And this person has received these 2 offers from these 2 different companies. And if you're very, well, if you don't think about this much at all, then you can then you might think, oh, these are basically pretty similar because they both have me making $32,000 in the first year, and by year 8 at both companies I'm making exactly $54,000 per year. But when you look more closely at the curves, you see that in offer 2, though you start at $32,000 a year, you quickly start making more. And then the rate at which your salary increases starts slowing down a little bit. Whereas in offer 1, you make $32,000 a year in the first year, but then you receive very slow salary increases, then it gets bigger later. Okay, so if we're simply looking at the problem from the perspective of what happens during the first 8 years, and not extrapolating to future events, then no, these offers are not the same. Because every single year, during this time interval, 0 to 8, you're going to be making more money per year at the job represented by offer 2 than the job represented by offer 1. Okay, and that seems kind of obvious, but this is actually a hot topic. Well, maybe I don't need to tell this story since we're not live, but this comes up a lot in salary negotiations, especially union salary negotiations, when there's a salary scale, such as the salary scale for our county, for teachers, and it is always in the incentive of the teachers to push for people to get larger salary increases earlier. Because then you're just going to be making more money. And here, the whole reason why we're talking about this problem right now is because in any given year, say year 3, the difference in the y values of these 2 functions represents how much more that year you are making in offer 2 versus offer 1. And so if you were to sum all these up, if you sort of think of that rectangle as having with 1, then your annual salary times the 1 year that you spend being paid that annual salary gives you the area of a kind of a rectangle, and that area of that rectangle represents how much more you made that year, that 3rd year, say, than from the offer 2 job versus the offer 1 job. And thus the area between these curves represents the total amount more money that you will make via offer 2 versus offer 1. Okay, so this problem is sort of in response to the question, which is quite reasonable, like, why should I care so much about spending hours of my life learning how to find the area between 2 curves? And one answer is that if these curves represent the rate at which things are changing, then if you have two quantities which are changing, so you have some quantity which is changing at a certain rate according to a certain, well, you have some function describing the rate of change of some quantity, and then you have some different function representing a different rate of change of that same quantity, then the area between those two curves represents the total difference in the net change of those two quantities over some period of time. And this is extremely important in things like econ and business and stuff like that. Okay, let's close that. Let's do 3 more problems, which are more of an abstract kind of just mathematical nature. 75, 93, and 94, all really hard. So these are all sort of interesting, challenging problems. So let's go. 75. See if I remember how to do this. 75 says, find B such that the line y equals b divides the region bounded by the graphs of the two equations into two regions of equal area. Yikes. So we are given y equals 9 minus x squared and y equals 0. Okay. So first of all, given that parabola and that line, there's some region which is bounded by those two equations. So step 1, let's get a picture going of that region so we can kind of reason about it. So here we go. I think I know exactly what this is going to look like. This is an upside down parabola. When you plug in 0, you get 9, and then 1, 2, 3, 1, 2, 3. Okay, and so I got something like this. All right. So I have this region, and then this is y equals 0. So great, beautiful little region we have here. Question: find a line y equals b, which divides this region into two equal area regions. Is that how the book puts it? Yeah. Find the line. Yeah. Find b such that the line y equals b divides the region bounded by the graphs into two regions of equal area. Okay. So the first thing to appreciate is that this thing is totally even, and so this making me go do both halves of it is just completely unnecessary. So I'm just going to delete the whole left-hand side of this graph and not talk about it anymore, because what I need to do is to find this mysterious line, and eyeballing it, maybe it looks like that. This is the line y equals b, which will divide this green region into two equal regions, and this line is going to also divide the full region into two equal regions because it's completely symmetrical. Okay, and because it's kind of fatter down here on the bottom than it is on the top, this line is not going to be, b is not going to be 4.5, right? It's going to be something less than 4.5, like 3.5 or something like that. Okay, how can we do this? Well, perhaps the best thing to do is to first find the area of the entire region. So let's do that. So what is the area of the entire green region? Well, it's going to be just the integral from 0 to 3 of 9 minus x squared. I only calculate the right-hand side, the positive side, because I've just completely ignored the left-hand side from now on, because it's irrelevant. Okay, so we do this, we anti-differentiate, we get 9x minus x cubed over 3, and then we just see what we get. And what we get is 27 minus 9, that's 18. Yeah, good. Therefore, and that seems very reasonable, right? If I were to put this parabolic region, this half of a parabolic region, into a box, it would be like a 9 by 3 box, so having area 27, so it seems very reasonable that this takes up 2/3 of that. In fact, that's kind of just what parabolas do, right? They take up 2/3 of their box. So this is certainly the right answer. Okay, so now, knowing that this is 9, I can simplify my life a little bit, and I basically can do one of two things. I need to find b such that this red region, or this region which I'm outlining in red, I need this to have area 9, or alternatively, I could find the area of this region down here such that it has area 9. And I think both of these are possible. And if I can solve either of these two problems, then I'll have my answer to what that y value is. Okay, I am going to solve the top one because I think that's more straightforward. Because after all, this region has a, I think, clear, simple method to partition it. And that method is to go up the y-axis from b to 9, taking an arbitrary y value and partitioning this interval up into a bunch of horizontal rectangles. If I add up the areas of all those horizontal rectangles, then I'm going to get the thing I need. Okay, so let's go. I'll do it right now, I suppose. Oh, well, a couple things I have to do first, which is that this curve is of the form y equals 9 minus x squared. So I need to solve for x. So I get that x squared equals 9 minus y, sorry, what was I doing? Oh yeah, and so x is root 9 minus y. Right, x squared is 9 minus y, so, okay, therefore, this parabola is represented by the curve y equals 9 minus x squared, but what we need is the a formula for the x-coordinate as a function of the y-coordinate, because I'm being given an arbitrary y value, and the answer is that for any arbitrary y value, x is just root 9 minus y. Okay, and therefore, certainly one way to do this problem is to integrate from b to 9 up the y-axis, and I'm adding up a bunch of rectangles. Each rectangle has length root 9 minus y and thickness dy. And what I need to do is to find for what b is this equal to 9. And that's the goal after all, is to find b. Okay, I think I can do this, but it is a little bit hard, especially because this root 9 minus y needs to be dealt with correctly. I'm going to be careful and do a u sub, so I'll let u be 9 minus y, and then I get that du dy is like negative 1, so du is negative dy. So I do need to stick in a negative here and to undo the damage on the outside. And, well, what do I get? I get that this is then root u, or u to the 1/2 du. But over here I get, there's a negative, but also I have to change my limits. So when y is b, u is 9 minus b, and when y is 9, u is 0. Okay, so I'll now flip this to get, to get the integral from, from 0 to 9 minus b of u to the 1/2 du equals 9. And okay, now I'll just do the integral. What is this integral? It's when I anti-differentiate, when I anti-differentiate u to the 1/2, I get up a power to 3/2, so this becomes 2/3 u to the 3/2, but evaluated at 9 minus b and 0 equals 9. Okay, so let's see, if I do some stuff, I'm running out of space, so I want to finish this. Let's multiply both sides of this equation by 3. So I think this is clear, right? Here I'm just doing the integral carefully with the substitution, and now I'm finishing off. I multiply both sides by 3/2. On the right hand side I get 27/2, but over here I get, I just get 9 minus b to the 3/2. Because when u is 0, that's just 0. So now I'm back down to the level of just algebra. There's still some work to do. I have to solve this kind of gross equation. So I get 9 minus b. If I raise both sides to the 2/3 power, then I get 27 halves to the 2/3. And you could leave it like that, I suppose. Or you could, 27 at least, I can raise to the 2/3. What's 27 to the 2/3? It's going to be the cube root of 27, which is 3, then square, which is 9. So that numerator is 9, and that denominator is, well, what's 2 to the 2/3? It's just the cube root of 4. And so I guess my final answer is that b is 9 minus 9 over cube root 4. And that sounds sufficiently familiar that I think it is right. Okay. And potentially I will just solve this entire problem over again the other way. So I think what's interesting about the other way, do I want to do that? Yeah, I wonder if this is what I even did would made any sense at all, actually, because, well, okay, I guess there are like 4 ways to do this problem, really, or 3 ways. I could have found the area of this red region horizontally, as I did, or, and maybe you were thinking this, why did you do it horizontally? Why didn't you just do it vertically? If you go to find the area of this red region vertically, okay, you can do that, but, and maybe that's easier because it's now a polynomial that you're integrating, but I need to know what that point is. What is that point? That's the point on the curve 9 minus x squared, whose y value is b, right? So this point is going to have y value b, and well, what do I have to plug into y equals 9 minus x squared to get an output of b? Well, setting y equal to b, this is like root 9 minus b. So if I plug root 9 minus b in there, then that's what I get. So, so the other way to do this problem, I guess, is to think of the red region as being partitioned with that black rectangle. And so now I'm going to be integrating from 0 along the x-axis to root 9 minus b. But now the thing I'm integrating is I'm adding up an infinite number of these black rectangles. And what are those black rectangles? They're 9 minus x squared. They have height 9 minus x squared minus b. So it's that. This is maybe like another interesting way to do this problem. This could potentially confuse some people because this is really like negative x squared plus, you should think of 9 minus b as being like a constant, because b is a constant. It's just something I don't know what it is. So really it's like that integral from 0 to root 9 minus b. Okay, and then we can just do it, right? This becomes negative x cubed over 3 plus, what's the antiderivative of 9 minus b? Well, it's actually 9 minus bx. And then all of that